Okay, yeah, thank you for your nice introduction and for the invitation to this wonderful workshop. And okay, I will speak about this very long thing, but I have a more simple title, which is Quantum 2D Material in a Subwavelength Cavity. And first of all, let me thank all my co-authors. So this work has been done in collaboration with experimentalists, mainly the group of Frank Coppens in ICFO, and with Marco Schirò and Marco Polini. And okay, this paper is out in archive, but let me give a very slow introduction on what we are interested in, and I guess all of you knows, but let me just re-say it. Quantum electrodynamics is the study of atom in contact with an electric field, and the light-matter coupling, the Rabi splitting is, how does it work? Like that. Is this omega Rabi, and is the electric field times the dipole, and usually this is applied when you drive an external electric field. However, we know that the electric field is a quantum mechanical object, so we can quantize it, and then it means that vacuum fluctuations are there even in absence of a pumping, so you can have finite effect. And once you do that, and if you quantize, for example, the electric field in a box, you will see that this light-matter coupling scale as 1 over square root of V. So this means that vacuum fluctuations are extremely weak in free space, so it's very hard to see anything. But there is this thing that is a cavity where you put mirrors to confine the electric field. I guess all of you know that. And since the electric field is this vacuum electric field is scaling like 1 over square root of V, if you compress the mirror, you get very high coupling. And then this means that you are kind of tempted to go to very small volumes. But somehow there is a complication that is what really is I'm interested in this talk, that is this diffraction limit. So basically, optics sets a minimum compression of the volume. So you cannot squeeze your cavity below lambda naught to the power of 3, and this is given by the frequency. Once you set your resonance, you cannot squeeze your cavity too much. And okay, let me give you some motivation why you want to go to strong coupling and to compressed light, because there are actually very interesting experiments going on, and we heard Jerome talking about electronic transport, but there is also this mysterious work that is still on archive after 7 years now, that is very debated about whether or not you can use like plasmon to alter superconductivity. And of course, I mean, in the past 10 years, we saw a lot of very interesting experimental work, a lot of theoretical proposal, for example, to change the topological property of a material, but then also these things about changing the superconductivity. And also I worked a bit on this topic where there is this photon-mediated or cavity-mediated superconductivity. So you know that in superconductors, the mediator is a phonon, which is a boson, but if you put the photon, it doesn't matter. It still mediates some attractive interaction. However, these are kind of extremely weird, extremely small, but there are some way where we think that this can be that can be increased. Okay, so, but let me give you a perspective of why this is kind of challenging, mainly because photons and electrons, they live on a different scale. So the photon is usually a delocalized object, which is delocalized like on 1 micrometer, like this, I'm talking about real photons, while an electron is usually have a length scale that can be around 1 nanometer. I'm talking about the Wannier function length scale. So And put in other words, let's say that we put a 2D material inside a Fabry-Perot cavity. The dispersion of the photon is this, the energy versus the Q parallel is on the XY plane. You can see that are these orange and red lines that are above the light cone. While excitation inside graphene or 2D material, they disperse on this Fermi velocity times Q, and since we are almost always in a non-relativistic setting, from the point of view of electrons, the situation is like that. So photons are when you are at finite Q, photons are immediately at very, very high energy. So electron and photons, they interact only at a very small region. And if you do the calculation on superconductivity mediated by photon, this is exactly the reason why at the end of the day, you will get extremely small number, like 10 to the minus 5 Kelvin for the critical temperature. And this is coming from, we have an analytical formula, but really the prefactor that kills everything is this guy that can be like 10 to the minus 8 easily. And this is the ratio between the cavity, the distance between the mirrors, so the cavity size, and A, which is the lattice constant. So somehow these really show this mismatch between electron and photon. And it seems that, I mean, there is no hope to measure something like that, because of course, even if you cool down your material to that temperature, which is almost impossible, then you will see appearing all other phase transition before that. So this is really hard to, this I think is kind of impossible to measure. But this is for a Fabry-Perot cavity. And then, of course, you can say, okay, but then what if I increase the field confinement? So I squeeze my cavity. And you cannot do it with Fabry-Perot because as you see, you can squeeze your cavity, but then all the photon will have more energy, so you will get no effect. But actually, you can go to sub-wavelength cavity. I will show you what they are. But basically, somehow it's like you put your photon in a medium which has a finite big refractive index, and then you get to slow down light, and then once this light is very slow, it can interact with electrons. So this is really the underlying idea of going to sub-wavelength cavity. And the problem is really that as long as you stick with Fabry-Perot cavities, so like mirrors and like air between two mirrors, you can do all the calculation, but as long as you stick to this kind of geometry, all your modes, they will fulfill the diffraction limit, and you cannot, for fixed frequency, you cannot go below this limit. However, if you search on the experimental literature, there is plenty of cavity. They do not fulfill this diffraction limit. And these are called sub-wavelength cavity. There are polaritonic cavities, plasmonic cavity, etc. And you can see that we can go even to 10 to the minus 8, 10 to the minus 10 mode volume, while still, okay, generally speaking, you have low quality factor, but there are still these hyperbolic photon polariton that they have still a very good quality factor compared to the graphene and to the split ring cavities. So sub-wavelength cavity, they can beat the diffraction limit, and they can achieve ultra-strong coupling between light and matter, but then this motivates us to really question if we have a good theoretical description. And yeah, and then with this paper, we realized that some part of the community was really using a working hypothesis that somehow can work sometimes, but is not totally justified. So basically, you want to describe your system in a sub-wavelength cavity, but you don't have a real theory for this kind of structure. So you do all your calculation in a Fabry-Perot cavity where the volume is V, and then at the end of your calculation you substitute the volume with the volume of the mode. So you rescale the volume by this factor, where lambda is the lambda of your subwavelength cavity, while lambda naught is the one dictated by the diffraction limit. And this guy can be up to the 10 to the minus 7 or easily 10 to the minus 10. And then at the end, this means that your coupling constant is rescaled by square root of A, and you can easily go from a prediction of 10 to the minus 6 Kelvin for superconductivity to 10 Kelvin.
Sorry, so the argument is we use the flat cavity and then we put in by hand ultra-strong coupling or spherical.
Yeah, exactly.
We shouldn't have, I mean, it wasn't justified, basically.
I mean, it was not justified. Sometimes it can work. I mean,
But not in our case. That's what you're going to tell us.
I mean, my statement is that we developed a theory that doesn't require this phenomenological argument. Then, I mean, to spot all the mistakes, I mean, I don't want to go in that direction.
More of a comment than a question. But so, in a sense, you could reason exactly analogously to your reasoning if I would try to mediate coupling between macroscopic order in a condensed matter system, for instance, charge density wave systems, where the size of the dipole which actually emits is a macroscopic dipole, and therefore you would reach this limitation. Would you agree with this statement?
I don't know if I...
So in a sense that you can go to this, let's say, sub-wavelength limit, but you can also increase the size of the electrons, taking a macroscopic order.
This is another thing.
But it would reason the same way.
Maybe you don't need this, but usually in many work to have very ultra-strong coupling, you need both. You need to have a sub-wavelength cavity, and you need to have collective variables. Okay. And then there is a trade-off, but for example, in the work of Jerome, this is the case. You have many Landau levels interacting with the cavity, and the cavity is small. So, I mean, because electrons are so small that there is room for having a collective effect and having a small cavity.
Just to make the point, whenever people do that, they would, of course, have to be very careful that at the zeroth order, you need to keep the number of particles that are interacting constant. Which is often why it's not the case. And therefore, your scaling never works like 1 over square root of A. Even in the best, I mean, even in that assumption.
Even if this is correct, yes. But I will show you an example where we don't have actually this scaling, but okay.
So, sorry, one question here. If you were going to answer it later, that's fine. But so the reason that this wavelength shrinks is that the photon is dressed with matter. So now my electric field does not live in the is shared basically. That single quantum is like half photon or a very small portion of it. It's photon. The rest of it it's matter oscillation.
Actually, we are going to see like a limit where basically there is almost no photon and is all matter. I mean.
And okay, good. Then I will wait. Thank you.
Okay. So, and actually, most of experiments are actually operating in this sub-wavelength limit.
Sorry, but by extension, the Ebdesing very debated is also in the same limit.
Right? I will say so.
No, not that I want to defend my honor. I'm just saying, like all these flat cavities are. So you're saying that one cannot argue smaller volumes regardless of the geometry.
Once you go to very small volume, you are sub-wavelength.
If you think about it.
If I just a comment on this, it's really a question of whether you're working in the longitudinal or transverse polarization. So if you're talking about like Ebdesing type of experiments, they're using plasmons but not extremely confined. So you could argue that in that case, this you're not using the subwavelength confinement as much. They have a bit of confinement, but it's not deeply subwavelength.
Repeat that?
So in the Ebbison experiments, they're using metal plasmons, which are very near, they're sort of near the light line, so they don't have extreme confinement.
So you're saying that basically all the action happens on some evanescent scale, close to the mirror, basically, where plasmons reside.
It's close to the mirror, but it's on length scales of it's wavelength scale close to the mirror. It's not 100 times smaller than the wavelength, which is where these arguments really kick in, and you get to TC of 10 Kelvin.
Yeah. So first thing that I want to convince you is that this subwavelength cavity, all of them, they have an electrostatic character, and this means that we can derive a theory which is based on this dyadic green function that I will explain in a moment, and that describe an arbitrary cavity, all kind of cavity, as long as you encode all the properties of the cavity, of the mirror, on the HBN that I will put in this dielectric function, and then you have a permeability function, and once you have these two, you write down equation of the Maxwell equation in matter, and you can characterize everything with this dyadic green function. So once you have like a dipole, so a current oscillating, this will excite your cavity and will produce an electric field. And this is, in linear responses.
Can I make one?
Yeah.
Just because you are making this dyadic Green's function, and you are saying that it's exact.
Well, it's exact.
It's just you assume the matter is in the linear regime.
Exactly.
And this is really important because every effect that we want to address in other phenomena is when you are not in the linear regime.
Yeah, but the game that I'm playing is that I define the cavity as a linear object, and then I will put later my material.
Yeah,
so for me, the cavity...
This is what you can prove that you cannot do.
Sorry?
Okay, doesn't matter.
Yeah, but it's on the linear thing, yeah. I mean, because there is only epsilon and mu that are the linear response, so I don't go beyond linear. And, okay, so this green function mediates the response. You have an applied field, and you have the response, and the green function fulfills the Maxwell equation, the Helmholtz equation. And actually, it turns out that, like, dividing things in the scalar potential phi and the scalar and the vectorial vector A, you can divide the green function in two terms. This is the scalar green function and the vectorial green function. And I will tell you in a moment the physical meaning of that. But what I mean, why is this decomposition is important? Because as long as you go to subwavelength cavity, you can estimate these derivatives as lambda, which is the size of the cavity, and you can see that in front of this green function, this is lambda naught divided by lambda squared, and this guy for subwavelength condition is very big. So basically, this means that that the green function of a subwavelength cavity is completely dictated by the scalar green function, which is solving the Poisson equation. So really, we prove that subwavelength cavity, they are dictated by the Poisson equation. And in the adiabatic limit, we can derive electron-electron interaction mediated by the cavity, and we can see that there are two types of electron-electron interaction, and in the adiabatic limit, so at zero frequency. One is the scalar part that is coming from electrostatic, and the other one is this vectorial that fulfills Biot-Savart law and is nothing else than magnetostatic. And this is only true in the adiabatic limit, but I will not stick to this limit, but it's just to give you a physical sense of what they are. This is electrostatic, and this is magnetostatic. At a finite frequency, this will be some finite frequency electrostatic, and this will be usual transverse electromagnetic.
When you go to finite frequencies, what do you do with the imaginary part of the electric response, the lifetime?
Sorry?
With the lifetime of the response functions, because you will get the real part and the imaginary part, and then this will introduce some additional decaying phenomena.
I will take into account that, yeah.
And how important it is?
Well, it's kind of, I mean, you will see, but it's kind of very important, yeah. Okay, so now let me focus on the description of HBN polaritonic cavity, which is this guy. So between two mirrors, now we put HBN, and this is for us is the cavity, and you can see that this has very good confinement and very good quality factor. And this HBN, as you saw yesterday, is an hyperbolic material, meaning that depending on the direction, you have two different dielectric functions, and there are these two regions that are very important, which are called the Strahlen band, where the product of the two epsilon is negative. And actually, we can solve the Green function for this cavity, and this is the form, and let me explain in a moment what this means. And basically, Q parallel is the momentum along xy on this direction, while Qz is the quantization on this. And this Green function has poles, so has excitation for when the denominator is 0 for this condition.
Sorry, maybe I should have asked this a slide ago, but are you doing this in zero temperature, finite temperature?
Zero temperature, yeah.
Okay. Yeah, okay, so just go on, thanks.
Okay. And you can see that we have poles for this condition, and we can plot actually the imaginary part. So this is the structure of the pole, the frequency as a function of Q parallel, and you can see that they are appearing in these regions, and they have this dispersion. And these poles are really dictated by this equation, and actually you can easily see that they are only there, which correspond to this gray area, because you can have, this can be true only if the two epsilon have different sign, because this is positive, this is positive, and they can sum to 0 only if they are different sign. And actually, we can quantize this cavity in order to quantify the vacuum fluctuation. And how we quantize it, we do an ansatz for the scalar potential. We say that the Hamiltonian is in the following form, so it's just a bunch of harmonic oscillator. At the end, everything is just linear. And once you compute the Green function with the quantum formalism, so using the Kubo formula, you can compare it with the one that is found by solving the Poisson equation, and by setting these two equal, we can determine the coefficient. So actually, you can calculate the vacuum fluctuation of this cavity. Sorry. And these are the vacuum fluctuation. Blue is for the upper Strahlen band, red is for the lower. And you can see that as long as you squeeze the cavity, for very long cavity size, you get this naive expectation 1 over square root of LZ, and then you get saturation, and after a critical value, the fluctuation goes to 0. So it's convenient to squeeze a cavity until it's no longer convenient. So there is a minimal size.
Is that an artifact of the gold layers that you assume?
The fact that there is this cutoff?
I don't know.
Because you force the field to go to 0, whereas if you had no gold, then this would not be the case.
Yeah, maybe it will just saturate, right? It will not go in different, but it will saturate to, it will not go to 0, but
no, I mean, it will saturate definitely, but the question is where. And
it's a good question. I don't know. Okay, and then let me make these remarks. So,
sorry, could I ask, is there any intuition for the length of the saturation? Like, how does it depend on parameters?
Yeah, if the question is where you saturate, you saturate of a scale that is given by 1 over Q parallel. So at a certain point, you lose the mode.
And kind of maybe an unrelated question, like, is a cavity like going to be affected by surface charges of the gold plate?
Sorry?
Like, is surface charge going to affect cavity properties?
Yeah. I mean, I will show you, but all the surface charges, imaginary, imaginary charges, they are there. I will show you later, if I manage. And okay, so, and
sorry, could you give some intuition for why the mode that you described as subwavelength?
Sorry?
Why is the mode that you described subwavelength?
Because it's just solving the Poisson equation. So if it's not in a subwavelength cavity, you can see that there are these Q parallel, these momentum that are very big. Sorry, where is it? No. This Q, you see, we are at these momentum are extremely big, so the resolution, the spatial resolution is very small. So this means that you can have this at given frequency only in subwavelength cavity.
Okay, thank you.
Okay, so, and let me say that first of all, you don't couple anymore with the vector potential that is widely studied, I mean, correspond to Paris phases, these no-go theorems that proves that it is stable and everything, but instead the coupling is different. So the coupling for this kind of cavity is mediated in this way, so you couple by the density, via the density to the scalar potential, and then you also have an additional, electron-electron interaction. They are really coming in these formalies together with the coupling with the cavity, and you can see that this green function is basically representing Coulomb, renormalized by the mirrors and everything. So you have a dynamical part and you have a static part that, funnily enough, is not the limit at zero frequency of the green function, but is actually the limit of infinite frequency of the green function. But still is a frequency dependent contribution, so it's kind of the static part. Okay, and then we put it in graphene, and we couple graphene with a magnetic field such that electrons go in circular motion, and the length is given by the magnetic length. And this Hamiltonian can be diagonalized, and you can see the transition, so this is the energy of the transition, as a function of this ratio, which experimentally you can manipulate it by tuning the magnetic field, and you can see that you have a lot of transition. They are not even in space like in usually 2D electron gas because of graphene that gives you the square root of n, but this is what you get, and you see continuous line are dipole allowed transition, and these the other one are non-dipole allowed. And let me also say the last few things about graphene in magnetic field. Since the interaction is like that, we compute the density-density response function, and this density-density response function depends on this matrix element related to the density operator that will be important later. And here we plot this density operator as a function of QLB, and the only thing that is very important here is that all these peaks, they correspond to QLB roughly 1, and this is chi, so the imaginary part of chi, and here you see the excitation associated with Landau level, and you can see that they are flat. And the intensity is really given by this matrix element. Okay, now let me show you the polaritons. So we couple these two systems. Here you have the cavity excitation, here you have the matter excitation. and then you couple it. You can either do RPA, so kind of classical thing, or you can write down the Miltonian. You get an opfield Miltonian, you diagonalize it, but this is what you get. So this is the combined spectrum, and you can see that inside the Strahlen band, the Landau level are hybridizing with the cavity, while outside there is this positive shift that is called the depolarization shift. I will comment later better. And another thing that you can do experimentally is rather following these Landau levels as a function of, by changing the magnetic field, you can control the energy of the Landau level, and you can see that here they will enter in the Strahlen band. And this is exactly what is happening. And you can see that there are, and white continuous line are dipole allowed, and these dotted are dipole forbidden. You can see that all of them, they are modified by the cavity. And you can see that here there is this hybridization that is coming from this part. So this is really a resonant effect. And actually you can, with this theory, you can really calculate the Rabi splitting, which is not exactly, no longer exactly a splitting, but this is the coupling constant of the theory. And you can see that it's just the vacuum fluctuation in the cavity multiplied by the square root of this matrix element. And this is really the formula that I showed you at the beginning by generalized to subwavelength cavity. And you can see that you need very high Q to get ultra strong coupling. So these are very non-local polaritons. And also there is a best LZ for the cavity to maximize.
Excuse me.
The cavity strength.
Question here. So Landau levels are with fermions, so you assume some filling factor, correct?
Yeah, this is at zero filling.
I see. And second question, could you explain these indices? Because in one of them, the Q is a good quantum number, right? For these plasmons. But then for this quantum Hall, what do you use as a quantum number? You have a Landau level index, and then you have this orbit indices. So is this Rabi frequency something in between them?
Sorry, let me say all the indices. So these indices are these minus 0, etc., etc. These are the indices of the Landau transition.
Very good.
Then this Q and the S, these are the indices of the mode. So the mode is in, I mean, you have...
It's in the Landau gauge.
Yeah, you have translational invariance, so you select the one, you see?
Okay, I can follow up, maybe you continue with it.
Yeah, maybe we can discuss it later. Yeah.
So can you comment on what actually goes into this model of electrons in graphene? So just free electrons, single particles?
Single particle electrons, but then the cavity, together with the cavity, you brings in Coulomb interaction, renormalized by the cavity. So there is Coulomb interaction here.
So the broadening, there are some broadenings of the level, so that's because of the...
No, this is due to intrinsic losses that you insert in chi.
So that's just a free parameter?
Yeah. So there is Coulomb interaction, but no losses associated with it. It's just RPA.
So just to understand that graph, let's say you would select one Q, and that selection of a Q would be made by, for example, a probe that would just scan and take kind of the amplitude.
Exactly.
And then you would see all those, each line corresponds to a crossing that you should be seeing somewhere.
Exactly.
Okay, thank you.
Okay, this is not something accessible experimentally.
Quick question.
This is it, but yeah.
Quick question. So you just mentioned that the interactions are coming through the cavity, renormalized Coulomb interactions. So then there is basically no this all-to-all interactions due to the cavity. It's just like long range with some range.
Yeah, I will say so, because this, I mean, I don't have like this flat mode. I mean, I have all the modes and I take all of them into account, and then I'm scanning, as Jerome was saying, at finite Q. So, and at the RPA level, I will not see something at Q.
That finite Q actually brings some
length. Yeah. These polaritons, they have a finite length.
Okay.
Yeah.
Okay. Thanks.
I mean, otherwise they are not very confined. Okay, and then you can see that somehow the cavity has another effect, that is this big positive shift also outside the resonant, and this is really coming from this depolarization shift that is really Coulomb interaction, but actually is this modified Coulomb interaction due to the cavity. So in free space you will not see such a big effect. And yeah, so with that I can conclude. Strong compression is possible only in this subwavelength cavity, but this subwavelength cavity have an electrostatic character, so you have to characterize with the Poisson equation, and I show you how to do the theory of ultra-strong coupling with magneto-excitons in these HPP cavities. And okay, with that, I thank you for your attention.
Quite a few questions, but time for a little more.
Thank you for the nice talk. Oh, sorry. So as an experimentalist, it wasn't clear to me, why do I need the metal layers when you're with a hyperbolic medium already?
Yeah, I already discussed this with Attach. I mean, actually there is no need, but it's quite better for the theoretical calculation. I mean, if you remove the metal, you can.
Because the hyperbolic modes should not couple to the free.
Confined.
Yeah, they're confined already.
But then just for the theoretical things, probably you could also have some propagating waves and stuff. So, okay. but I mean, they are not essential. You can remove it.
Okay. Yeah. Thanks.
So thanks. Very nice talk. I like this approach. So, but I guess. My questions are mainly about resonance effects, because we've seen in similar calculations at finite temperature, you do essentially the same, but with Matsubara-Green's functions. And there, when you analytically continue, your real frequency to I omega, all of the resonances go away. Anything that's a 1 over omega squared minus omega naught squared becomes positive definite. And for instance, hyperbolic phonon.
At all temperature?
Yeah, you have to, I mean, it's like a property of, analytic continuation. So I don't know how you can, so for instance, in the hyperbolic phonons where you have this sign changes in epsilon that is very important, it just completely disappears in the calculations. So I don't know if, how does this...
I mean, but people have seen this kind of signature.
In a response function or in like a an expectation value? Because it shows up in response functions when you analytically continue, but if you calculate the expectation value of some fluctuations or some order parameter, you sum over Matsubara frequencies and everything is always positive. And so I'm wondering actually...
I didn't know, but we can certainly discuss about it.
Okay, thanks.
Mohammed?
So I will go back to my question now because you finished your talk. So on the plasma side, you have a dispersion relation. It's an omega versus Q, right?
Yeah.
And then on the Landau level, you have energy versus, let's say, Q or angular momentum, whatever index you like it to be, right? So when I'm is that clear?
Yeah.
So the x-axis is some space, right? Then you couple them.
Mm-hmm.
So in principle, any of these photonic mode can hybridize between two Landau levels. So I get not just one index, I would get two indices. If I don't add disorder, things like that, in principle, between two Landau levels, I can take any electron from here and then put it over there. Does that make sense? Because the right-hand side is not the excitations of the system. These are the eigen values of my electronic system. So I can do any transition. You can think of it as a very complicated atom that can have many transitions.
Right. But
so then
I probably sum over them. No, I mean, what I mean is that at the end, the excitation of my materials, they are given, my combined material, that are given by RPA equal to 0, epsilon RPA equal to 0, and you can see that here you have Q parallel, here you have Q parallel, they are the same Q parallel, no? This is what I mean. It's like you, at the end, all the spectrum are corresponding to the fact that you come with a SNOM tip, which has Q parallel, that sets a Q parallel, and then you see the response. This is what I mean. So the Q parallel is the same for the density response function and for the scalar Green function. But I mean, I got your point, but this is a physical kind of response function. So.
Can I just bring the conversation lower, just a naive experimentalist questions? I didn't understand where the nonlinearity came in the sense that you did.
What do you mean nonlinearity?
So in a sense, this is all linear response.
Yeah. There are no nonlinearities in the problem.
Okay, and then what's the feedback on the cavity? So what is the? I mean, if I calculate this with the transfer matrix language, I will get the same result.
With epsilon and everything, I would say so. Yeah.
Okay.
Yeah. I mean, this COMSOL simulation that people do with transfer matrix. I mean,
so it's all linear. It's all linear response.
At the end, is very accurate. Yeah. For this kind of system, yeah.
This is no. I mean, what you show is an extremely complex. And I understand probably why, because of course you have all those, you don't have this so strong selection rule between the Landau levels in the graphene, and then you have this zoo of modes in your hyperbolic boron nitride. Intuitively, do you believe something collective might arise in the transport, or is that your hope, obviously?
Yeah, this is the goal of Frank and all of us.
Right.
We are doing that, so we hope for that. I mean, but for example, is not the ultra strong coupling is barely reached.
Yeah.
So, and I mean, I guess that this boils down to what you were saying yesterday, that maybe graphene doesn't have all the magic parameters to have all the best interaction, but besides that, I mean, I think that it was nice that we developed a generic
sure, obviously. And that is already, of course, what you plotted, I assume, is for an optimized cavity where you have kind of the strongest light matter coupling.
Yeah.
Thank you.
And we could do that because we were able to extract all the parameter by this theory, right? I mean,
right, exactly.
Yeah, this formula is. Sure. I mean, if you, because before, with the transverse matrix method, you have this guy and Matteo, when he got that with transverse matrix method, he was saying, okay, what I do with that? Sure. Do I do a split? What I do? Sure. And then this is why you need all these theories.
Thank you.
I'm wondering if you actually go back to the previous slide, you were showing results for 5 Tesla, which is approximately 80 milli-electron volts, roughly, and significantly lower than the so the Landau level spacing is much lower than the photon energy for these polaritons. I'm wondering what happens when it becomes resonant.
No, it's resonant. You see, these are all the Landau levels, and you see that some of them, for example, these guys is somehow here, right? You see, this is the Landau level. Do you see it? This guy is the Landau level hybridizing.
Okay.
So you are right in the sense that the second Landau transition, they are not in resonance with anything, but there are some Landau levels. This is due to graphene. Graphene is a huge mess, and then you always have something.
But those higher order Landau levels, I would imagine, are also have different selection rules because they have different chiral.
Usually, but you see, this is at such a big Q that you don't care about selection rule. Selection rule are for dipoles matrix, but here you have all these exponentials, so you basically don't have this selection.
Okay, so let's take the remaining questions to coffee break. Thanks, John.